unit review conversion practice that I gave you guys in preparation for your unit test on Thursday. As we can see above here, we've got this table that shows our different conversion factors that we'll have available to us to solve the problems. This will be on the front page of the test if you think it's helpful. So let's take a look at the first question here. So question 1 asks us to give the number of helium atoms in 2.00 moles of helium gas. So if I start by listing my things that are given, I can see that we're given 2.00 moles of helium gas. Is that big enough for you guys to read? I think so. Okay, cool. And in addition, we're required to find how many helium atoms there are. So it's the number of helium atoms. Okay, that's our required. Those are the first two steps in grapes. Obviously, we could draw a picture of this for an art step. But I only have so much time, and there's lots of questions to get through. So if you want to do that on a test, that's definitely worth some number of marks, even if you're not sure what to do after that. If you can visualize it for me and draw me a picture, that'll get you part of the way there. And I recommend you do so if you're not sure what you're doing, which happens to everybody from time to time. Okay, so I know I've got moles of helium gas. That's my starting value. So what I suggest you try to do is locate where we are on our heart of the mole sheet to kind of get started. And it says we're starting here with moles. We know we have 2 moles of helium gas. And we want the number of helium atoms. So we look and we say, okay, atoms are a type of particle. Now I believe on your heart of the mole sheet we use the word things. This was the only one I could print off handily today for boring logistical reasons. So anyway, we're going to use this conversion factor here and turn our number of moles, cancel that, and turn to some number of our particle, which in this case is atoms. And so a more appropriate unit conversion factor is actually listed up here because it actually is a conversion factor into a number of atoms over a mole. Now, what lives here depends on what we're talking about. In this case, helium is just an individual atom. Okay, so we always start with our given value. Sometimes we're given multiple values, and that can make it a little difficult. In this case, we're only given 1, so that's our starting value, 2.00 moles helium. And I'm going to convert that number of moles using this conversion factor on the left here, because I want to cancel out my units of moles diagonally. So that's I'm going to put 1 mole of helium down here. And up above, we've got 6.02 times 10 to the 23 atoms of helium. I take my pen and I make sure all units I'm not looking for cancel out. And the only units left are atoms of helium. And if you look here, that's what we were looking for, number of helium atoms. So the last thing I do is I grab my calculator. I say, okay, this looks like a pretty straight multiplication. So 2.00, you can put 2.00 in your calculator, but it doesn't know the difference between 2.00 and 2. And multiply by 6.02 times 10 to the 23. And we get 1.204 times 10 to the 24. We have 3 sig figs here, 3 sig figs here. So we're going to round that to 3 sig figs. 10 to 24, and our units are atoms of helium or helium atoms. I like to put a big box around my answer. Alright, let's move on to the next question. So this question is actually kind of a 3-parter, and we're going to get to those second 2 parts in a bit, but we'll just start with the first part here. So first, we're given, so our G, the thing we're given in this case, is we've got 3.56 moles of carbon dioxide gas. And our required value is, we're looking for the number of carbon dioxide molecules. So that's the number of CO2 molecules. Okay. So first thing we'll do is, it looks like actually we've got a really similar situation to the one we had in the last example. Again, we take a second to locate where we're beginning here, and we're going to begin here on the moles, and we're looking for a number of, in this case, number of molecules, which is another type of particle. So we're going to use that same conversion factor we did above. So that's the first one. I think I'll use blue for this. 3.56 moles CO2, and we'll just use the same conversion factor here. Now the difference being, we're talking about molecules this time. Molecules CO2, and we're going to divide it by 1 mole of CO2. And our moles cancel out. And again, we end up with a straight multiplication here. Again, very similar to the last question. So I'm kind of rushing through this one because I feel like we went over a really similar example in question 1. And so then we got 2.14, 3 sig figs, because again we had 3 sig figs here and 3 sig figs here, times 10 to the 24 carbon dioxide molecules. Okay. Now, we should put a box around that, but then recognize we actually had a little bit more to this question. So we're actually also asked something further. We're asked how many carbon atoms are in a mole of carbon dioxide gas. So I'm going to make a little A here and say, okay. In this case, let's be careful, we're asked about a mole of carbon dioxide gas. So we'll start there. We'll start with 1 mole of CO2. And we're not asked for the number of molecules, we're asked for the number of carbon atoms. Now, in a question like this, we have to recognize that if we're talking about a mole of carbon dioxide, which we are, this conversion factor will only tell us the number of carbon dioxide molecules we have. It won't tell us about the carbons or the oxygens directly. But we are given a diagram here. We can see that a carbon dioxide molecule has 1 carbon atom, but it has 2 oxygen atoms. I should put an X there so it doesn't just look like the number 20. Maybe I should, it still looks like 20 times now, so oxygen. Okay, so we're going to use this information to make a new ratio that is not on our heart of the mole sheet. But first, we need to get to the number of CO2 molecules. So we're going to use the same conversion factor we used in the last 2 questions. 6.02 times 10 to the 23 molecules CO2 over 1 mole CO2. And again, we get those units to cancel out diagonally there. We've got molecules now. And we know 1 molecule of carbon dioxide gives us 1 atom of carbon. So there's 1 atom of carbon in every 1 molecule. So I can make another conversion that cancels out units of molecules. I'm just going to write, no, I'll write the whole thing. CO2. And I know 1 molecule of CO2 has 1 atom of carbon. And then lastly, I just check to make sure molecules cancel out, and they do. And if you look at this operation here, it doesn't look like there's really a lot of math to do in a calculator. I multiply 1 by 6.02 times 10 to the 23 times 1 divided by 1 divided by 1. Well, that's not really going to change anything, is it? So I'm just, rather than pick up my calculator, I'm going to just write 10 to the 23, Avogadro's number. But my units here are now atoms of carbon. Okay. Now the next question is very similar, but it asks us for the number of oxygen atoms in a mole of carbon dioxide gas. So again, we're still talking about a mole of carbon dioxide gas, but instead we're talking about oxygen atoms. So the only thing I really wanted you to do here is really appreciate, in kind of a really simple example, the difference between answering how many carbon atoms there are in a molecule, how many molecules there are, and how many, in this case, oxygen atoms there are. So I'm going to start in the same way, 1 mole of carbon dioxide. And again, same thing, we need to go from moles to some number of actual molecules in this case. 6.02 times 10 to the 23 molec CO2 over 1 mole CO2. My units of moles of carbon dioxide cancel out diagonally. And then I need to know that 1 molecule of carbon dioxide has 2 oxygen atoms. So my last conversion factor here is going to cancel out units of molecules of CO2. And for every 1 molecule of CO2, there's 1 atom of carbon, but there is 2 atoms of oxygen. So then I put 2 atoms of oxygen up here, and then these guys end up canceling out diagonally, these molecules of carbon dioxide. And here you can see the really only operation to put in the calculator is our Avogadro's number, 6.02 times 10 to the 23 times 2. And you might ask, how many sig figs should we be rounding to? Well, this Avogadro's number that we use tends to have 3 significant figures. This is we know more, actually, the sig figs than we tend to write. But so for Chem 11, 3 sig figs is fine. And this is an infinity number of sig figs. There isn't around 2 oxygens for every carbon dioxide. There's exactly 2. If there was more than 2 or less than 2 oxygens, it wouldn't be carbon dioxide, it would be some other molecule. So in this ratio, these molecular ratios are exact. Okay. That means we're going to be restricted by these 3 sig figs here and get 1.20 times 10 to the 24 atoms of oxygen. Oops, of oxygen. All right, let's move on. So next question says, if the Pacific Ocean has 2.4 times 10 to the 46 water molecules. So we'll just write that down. Pacific Ocean has 2.4 times 10 to the 46 water molecules. How many moles of water are there? Molecules. How many moles of water molecules? Okay. So the first thing I'll do is I'm going to write down the given value here. So I'm starting with 2.4 times 10 to the 46. And I find writing H2O is faster than writing water molecules. And that, if I look on the sheet, is some number of things, in this case, water molecules. And I want to go to the number of moles. So I'm going to use this conversion factor that along this arrow that converts a mole of things, or turns a mole of things. I'm not saying that very clearly. Cancels out our units of particles and replaces it with units of moles. Okay. So I'll use that conversion factor. So 1 mole of water molecules. And on the bottom is 6.02 times 10 to the 23 H2O molecules. And my water molecules cancel out. And then I have this conversion here. Alright. Now, this is where actually you need to be very careful about how you type this into your calculator. If you use either an exponent button on the bottom of your calculator here, or if you have a Texas Instruments calculator, like there's a little EE usually around here above the digits, to do exponent notation or scientific notation, then you should be fine. If you don't, you will need brackets when you divide by Avogadro's number. But you probably figured that out already. All right, 2.4 times 10 to the 46. And I'll divide that by 6.02 times 10 to the 23. And I get 3. Oh, I should get how many sig figs? 2 sig figs here. 3 sig figs. So my answer should be rounded to 2 sig figs, which means I would have to round that to 4.0 times 10 to the 22 water molecules. Oh. Nope, those aren't the units, because the units are moles of water molecules. Okay. Oops. Now, that hopefully makes sense. It's how many handfuls of water are in the Pacific Ocean? Well, I don't know the answer, but it's probably a lot. Water molecule, or handfuls of water, are very small. I think it worked out about 18 milliliters or so if we measured in class. And you can imagine it would take you a real long time to fill up the whole Pacific basin with those little 18 mil drops, because you'd be dropping this many in. That's a lot of handfuls. Right. Let's move on to question 4. So question 4 asks how many moles of magnesium are in an aerosolized cloud of 4.5 times 10 to the 20 magnesium atoms. Okay. So again, looks like the thing that we're given is some number of magnesium atoms. So, and there's only one thing we're really given, so I'll just write that down. We got 4.5 times 10 to the 20 magnesium atoms. Now, before I go any further, moles are a number of handfuls of atoms, right? And it looks like I've got not very much compared to, say, Avogadro's number, which is a handful. So it looks like I should be expecting maybe 1/1000th of a handful when I'm done this calculation. Right. And so to go from atoms to moles, again, this is this conversion factor here. I start with some number of atoms, and I'm going to convert along here to moles. So 1 mole of magnesium atoms over Avogadro's number, 23 mg atoms. Okay, and our magnesium atoms cancel out. And again, we just got 4.5 times 10 to the 20 divided by, oops, there's a lot of glare there, you can't really see that, divided by 6.02 times 10 to the 23. And again, we're going to round to 2 significant figures, so we should get 7.5 times 10 to the negative 4 magnesium, no, I should say moles of magnesium atoms. Or I could expand that, I could say it's 0.12375 moles of magnesium atoms. Oops. Okay. So let's continue. Okay, finally we're gonna maybe do something a little bit more complex, because really for these last 4 questions all we've been doing is really going back and forth along this path. And now finally we have another quantity. We're talking about a mass of aluminum. So the question here is how many aluminum atoms are there in a 3.7 gram empty Coke can? Okay, so I know that I'm going to be starting with 3.7 grams, and that is made of aluminum, so I'm going to say of aluminum. Okay, and so if I look where I'm beginning on this sheet, I know I'm starting here is a mass. I know the mass of the Coke can, and I want to know how many atoms, how many particles there are to construct that whole can. So to do that, it looks like I have to do a two-step conversion. And if I look in this conversion, it says I have 1 mole at the top, but I need the molar mass of my substance, which in this case is aluminum. So the first conversion factor will turn into 1 mole of aluminum. In exchange, I have to find the molar mass of aluminum. And to do that, I'm going to use my periodic table. Now, I actually don't have a printer right now, but I did have a textbook lying around. This is my Hebden textbook. And I look for aluminum on this periodic table here. And I can see aluminum's right here. It's got a molar mass of 27.0 grams for every mole. So that's the molar mass. So for every 1 mole of aluminum, in other words, it weighs 27.0 grams of aluminum. Okay. And that gets us here, and now to get us the number of atoms, we're going to use Avogadro's number. 6.02 times 10 to the 23 atoms of aluminum for every 1 mole of aluminum. And if we check, their units of grams cancel out, our units of moles cancel out. We've got units of atoms, which is what we were asked for. Okay, so we just grab our calculator. We say, okay, we've got 3.7 times 1, which I don't need to write, times Avogadro's number, 6.02 times 10 to the 23, and I'm going to divide by my 27 here. So I divide that by 27. And overall, I should get 2 sig figs is what I'm going to round to because of this guy. That's a 3 and 3. So it's going to become 8.2 times 10 to the 22 atoms of aluminum. Okay, last question on the page. Cloud is composed of 3.5 times 10 to the 31 water molecules. And we want to know how much the cloud weighs. So again, look in here, where are we starting? Well, we say we have some number of water molecules. That's a number of particles. So we're starting here. We want how much the cloud weighs. And weight, because we're in chemistry class, we treat weight and mass to be roughly the same thing. So we're going to try to get down here. So we're going to retrace our steps, go in the opposite direction that we did in question 5. All right. So I'm going to start here just by writing down that I start with 3.5 times 10 to the 31 water molecules. And the first thing I'm going to do is I'm going to turn that into a number of moles. So everything always goes through the mole. So we go here, we're going to cancel out our units of water molecules. So 6.02 times 10 to the 23 water molecules. And above, that's just 1 mole of water molecules. And our water molecules cancel out. That's fine. Now, to move from mole to mass, looks like I need the molar mass of water. That'll be in grams per mole. So to find the molar mass of water, I'm going to find the molar mass of water here. So I'm going to look at my periodic table and say, okay, for my H's, I've got 1 times 1.0 grams per mole. Oh, no, sorry, I've got 2 hydrogens in water. And I've got 1 oxygen, so it's 1 times 16.0 grams per mole. So overall, it's going to give us 2.0 plus 16.0. And I look and I say, okay, that'll give me 18.0 grams per mole when I'm done. And so I'm going to use that value here. I get 18.0 grams of H2O for every 1 mole of H2O. And if I check, I see, okay, what units didn't cancel out? Well, I get units of grams, which is a weight, which is what I wanted. And we're going to find out how much a cloud weighs. So 3.5 times 10 to the, oops, 5 times 10 to the 31 divided by 6.02 times 10 to the 23. And I'm going to multiply that by 18. And it looks like a cloud weighs, a really big cloud weighs about 1,000,000 grams, or 1,000 kilograms, about a metric ton. Of course, I want to round that to 2 sig figs, so the only way to do that is to say it's 1.0 times 10 to the power of, oh, you know what, I missed that decimal place. That looks like it's 1,000,000 tons, not 1,000 tons. Anyhow, 1, 2, 3, 4, 5, 6, 7, 8, 9. So times 10 to the 9 grams of water. That's my answer expressed to 2 significant figures. That's a heavy cloud. Oops. All right. So let's move on to the next page here. So the next page is about Coca-Cola. Question 7. So it says Coca-Cola contains carbon dioxide. That's fine. If an, there should be a space there, open can of Coke is left to go flat, it will release about 385 milliliters of carbon dioxide gas. Okay, so that sounds important. 3.85 milliliters of carbon dioxide gas at standard temperature and pressure. Okay. So it looks like we have a few parts here. Let's start with how many molecules are of carbon dioxide are in an unopened 355 ml can of Coke. Huh, okay. So all cans of Coke are 355 mils. All right, so where are we going to start here? It looks like we've got a lot of information. So once we start having lots of information, maybe it's a good thing to do, just turn to grapes so we don't get confused. So let's talk about the things we're given. We're given that we've got a 355 ml can of Coke, 355 ml Coke can. Okay. What else are we told? We're told that that gives us 385 mils of carbon dioxide if you open it, of carbon dioxide when it's opened and released, right? Oh, we're also told that it's at STP. Okay, then maybe that'll come in handy. We're not sure. All right, and what are we required to find? Let's be specific with our required step here. Question asks us how many carbon dioxide molecules. Okay, so we're looking for a number of CO2 molecules in a can of Coke. Okay. So, looks like we're given a lot of information here. Where should we start? Let's pretend that we aren't sure. Okay, so I might actually draw a picture. So, next thing I'm going to do is I'm going to just draw a can of Coke and try to connect all these pieces of information. So there's my can of Coke. Wonderful drawing, thank you very much. And I know that if it's unopened, first of all, this whole thing is a 355 ml can, right? And we know it contains carbon dioxides. And they're kind of stuck inside that solution. And when opened, all those carbon dioxides form a cloud. And that cloud is approximately the same volume as a can. It's maybe a little larger, actually, because gases tend to occupy more space than liquids. Okay, and that is a 385 ml of carbon dioxide, and that's only considering we're at STP. Okay, so that helps me picture kind of what's going on here. And what if I'm looking for the number of carbon dioxide in an unopened can of Coke? I'll need to start with maybe this value here, because I know this is a value about the carbon dioxide. This 355 mils, that just tells me we're talking about a can of Coke. This is the value that tells me about the carbon dioxide. So that's going to be my starting value, 385 mils of carbon dioxide, and that's at standard temperature and pressure. So that tells me it's a volume of a gas. So we're starting over here this time. And what are we required? We're required to find the number of carbon dioxide molecules in a can of Coke. So that's the number of particles. So we're going to need to go from down here up to here. And before we get started, we need to make sure we are starting with liters of our carbon dioxide gas. So the first thing I'm going to have to do is make sure I've turned this number of milliliters into a number of liters. So I know 1 liter of carbon dioxide is the same thing as 1,000 milliliters of carbon dioxide. And so milliliters of carbon dioxide cancel out. So now I've got liters of carbon dioxide. And now I can turn it into a number of moles of carbon dioxide using this conversion factor. So I know 1 mole of CO2 is the same, occupies 22.4 liters of space at standard temperature and pressure, which we know we're at. And lastly, we need to turn into a number of carbon dioxide particles, which is going to go from here to here using Avogadro's number. 6.02 times 10 to the 23 CO2 molecules for every 1 mole carbon dioxide. Alright, so we'll punch these guys in. 385 multiplied by 1, multiplied by 1, multiplied by 6.02 times 10 to the 23. And then we're going to divide by 1,000 and divide by 22.4. Tough to find a place for this calculator without the glare, and when I finish, it equals 1.0346875 times 10 to the 22 carbon dioxide molecules. And I check how many sig figs. Looks like I have a 3 there. This is a fixed value. This is infinity sig figs. 3 sig figs. So we should be rounding to 3 significant figures. So looks like we got 1.03 times 10 to the 22 carbon dioxide molecules. And that's in a single can of Coke. Okay, I think there's another couple steps here, so let's finish this question off. So that's A. That's A. I'll just write that here. Alright. So 7B builds on that. It says, okay, how many oxygen atoms are there in an unopened can of 355 ml can of Coke in an unopened 355 ml can of Coke. Okay. Well, to do that, looks like we've done most of the hard work already. We know the number of molecules, and we know there's 2 oxygen atoms in every 1 carbon dioxide, right? So I could just take this value that I found, and because I know that for every 1 CO2 molecule, that's 2 oxygen atoms. Okay. So I'm going to start with this value here, which is 1.03 times 10 to the 22 molecules CO2, and say there are 2 oxygen atoms for every 1 CO2 molecule. And molecules of carbon dioxide cancel out, and I get units of oxygen atoms. So I'm going to take this number, which I actually still have in my calculator. I'm just going to multiply it by 2. And I'm going to get 2.07 times 10 to the 22 oxygen atoms. Now, you might have got 2.06 if you had this written down explicitly, as opposed to having that value in your calculator. And that kind of round-off error is something I'm not going to worry about on a test situation. But strictly speaking, if you were to do this calculation, you really should start from here, do all these conversions, and then one more. That way, you always keep the correct number of significant figures correct to the last decimal place. Anyhow, I wouldn't worry too much about that, though. Okay, last question. We want the mass of carbon dioxide in an unopened can of 355. An opened 355 ml can of Coke. Okay, so looks like we're going to, again, start here. Instead of heading up in this direction and maybe turning into a number of oxygen atoms as we did, we're going to go down and find the mass of that carbon dioxide. Looks like to do that, we're going to need to know the molar mass of carbon dioxide. So I'm going to start with the molar mass of CO2. So starting with my carbon, I've got 1 times 12.0 grams per mole, and I get that from my periodic table. And my oxygens, I've got 2 times 16.0 grams per mole, right? And so that just gives me 12.0 grams per mole plus, and I get 32.0 grams per mole here for the oxygens. And I add them together, and I get 44.0 grams per mole. And that's for carbon dioxide. Okay, great. So, I'm going to start with our 385 mils of carbon dioxide gas. 385 mils of CO2. I need to turn that into liters. 1 liter CO2 for every 1,000 mils. And then I need to get from here to my number of moles. So I'm going to use my volume, my molar volume here, and so it says that 1 mole of carbon dioxide occupies 22.4 liters of space. I'm going to stop part way and just make sure all my units cancel out, milliliters cancel out, liters cancel out, and then I'm going to stop and say, okay, for moles, I'm going to find my mass. So I'm going to use my molar mass, 44.0 grams for every 1 mole of carbon dioxide. 44.0 grams of carbon dioxide for every 1 mole of CO2. And I'll just grab my calculator and say I've got 385. And I just multiply across till I get to 44. And then I'll divide by everything on the denominators here. So I might divide by 1,000. And I'll divide by 22.4. And it looks like all the carbon dioxide gas in a can of Coke only weighs, well, less than a gram. Still, it's quite a bit. 3 sig figs. It looks like we're onto 3 sig figs. We get 0.756 grams of carbon dioxide gas. Okay, we'll call it there for now. But you can find the next series of questions on Google Classroom. Good luck studying, guys.